You know how in chemistry class they tell you that chemical bonds are either ionic or covalent? Well, what if I told you some bonds are leading a double life? What if some of them have a secret identity, pretending to be ionic, but secretly acting, well, a lot more like they're covalent? Today, we are going to unmask the hidden rules that govern these chemical double agents.
So let's just dive right in with a bit of a puzzle. On the one hand, we have sodium chloride. Yep, regular old table salt. On the other, we have silver chloride. Now, both of these look like your classic ionic compounds, right? A positive metal ion bonded to a negative chloride ion. But just look at their melting points. Sodium chloride melts at over 800 degrees Celsius, while silver chloride melts at 455. That's nearly half. What is going on here?
So what gives? On paper, they look so similar. But in the real world, their properties are just worlds apart. Why is there such a massive difference? This is one of those fantastic little contradictions in chemistry that tells you there's a deeper, much more interesting story to uncover.
And the answer to our puzzle, the key to this whole mystery, is a hidden force called polarization. This is the secret mechanism, the little trick that allows an ionic bond to basically put on a covalent disguise and act completely out of character.
Okay, so let's go back to the textbook for a second. In theory, a pure 100% ionic bond is a super simple transaction. One atom hands over an electron completely to another atom. Bam! You're left with a perfect little sphere of positive charge and a perfect little sphere of negative charge, just hanging out together because of electrostatic attraction. It's clean, it's simple, and well, it's not quite the whole story.
See, in the real world, things get a little messy. That positive cation just doesn't sit there politely. It actually exerts this powerful pull on the electron cloud of its neighbor, the negative anion. So instead of being a perfect, untouchable sphere, the anion's cloud of electrons gets distorted, warped, pulled toward the cation.
And this distortion, this warping, it has a name. It's called polarization, and this is the absolute key to everything. The cation tugs on the anion's electron cloud, pulling it so close that the electrons actually start to be shared between the two atoms. And what do we call a bond with shared electrons? That's right, a covalent bond. So this polarization introduces what we call covalent character, and that's how an ionic bond gets its secret identity.
So, the big question is, how do we predict how much of a double agent a bond is going to be? Well, lucky for us, a Polish-American chemist named Casimir Fajans figured it out. He came up with a set of guidelines, which we now call Fajans Rule, and they're basically our spy manual for predicting a bond's secret covalent side.
All right, rule number 1 is all about the cation's size. Think about it. A smaller cation, like lithium, has to pack its entire positive charge into a tiny little space. This gives it a really high charge density, and that means it has a super strong pull, what we call high polarizing power. A bigger cation, like sodium, has its charge all spread out, so its pull is a lot weaker. The bottom line? Smaller cations make for better spies.
Okay, on to rule number 2, which flips things around and looks at the anion size. A really large anion, like iodide, has this big kind of fluffy electron cloud. Its outermost electrons are far from the nucleus and aren't held on very tightly, so they're easily distorted. But a small anion like fluoride, it keeps its electrons in a death grip, close to the nucleus, making it really hard to polarize. So, in our little spy game, bigger anions are much easier targets.
Rule number 3 is probably the most intuitive one. It's all about the sheer magnitude of the charge. A cation with a +1 charge, like our friend sodium, gives a pretty gentle tug. But a cation with a +3 charge, like aluminum, whoa, that exerts a seriously powerful, almost violent pull on the anion's electrons, causing a massive distortion. It's simple. The higher the charge, the more covalent character you're going to get.
And this brings us to the final rule, the special case that solves our original puzzle. Meet the superhero cations. See, cations like sodium have a stable 8-electron outer shell, a noble gas configuration. But cations like silver have what's called a Pseudo-Noble gas configuration, with 18 electrons. And it turns out those extra d electrons are absolutely terrible at shielding the positive charge of the nucleus. So even though silver is about the same size as sodium, it's a vastly more powerful polarizer. It's a true super spy in the world of ions.
Okay, so we've got these rules, we can predict a bond's secret identity, but who cares? Why does any of this actually matter? Well, as it turns out, this shift from ionic to covalent character changes a compound's properties in really dramatic, real-world ways.
First up, melting points.
Pure ionic bonds form these super strong crystal lattices that take a ton of energy to break apart. But as you introduce more covalent character, those forces between the molecules get weaker. Just look at the lithium halides here. As we go from the small fluoride anion to the big iodide anion, the covalent character increases. And what happens to the melting point? It absolutely plummets.
Next up is solubility. You've probably heard the old chemistry rule, like dissolves like. Well, polar ionic compounds absolutely love to dissolve in polar water, and nonpolar covalent compounds, they prefer nonpolar organic solvents like oil or benzene. So it makes sense that as a bond's secret covalent identity gets stronger, it becomes less soluble in water and more soluble in organic stuff. This is exactly why silver chloride is so much less soluble in water than our good friend sodium chloride.
And now for what is, I think, the most visually striking consequence of all. Intense polarization can actually make a compound colorful. It all happens because distorting that electron cloud changes the way the compound absorbs and reflects light.
Check out this incredible example. On the left, you've got mercury chloride. It uses the smaller chloride ion, so it's less polarized and is just a simple white solid. But on the right, mercury iodide involves the huge, super easily polarized iodide ion. The polarization here is so intense that it turns the compound this vibrant, beautiful red. Same metal, different halogen, totally different appearance. It's amazing.
Phew, we've been through the puzzle, the theory, the spies, and the consequences. So let's bring it all home and boil it all down to one simple, easy-to-remember formula for predicting a bond's secret covalent side.
Here it is. This is the recipe for getting the most covalent character you can. You combine a small cation with its concentrated charge, a large anion that's easily distorted, and you crank up the charges on both of them for the strongest pull. That combination, small cation, large anion, high charges, that's your key to unmasking the bond's hidden covalent identity every single time.
So it turns out no bond is ever really 100% one thing or the other. They all exist on a spectrum. The world of chemistry is just filled with these chemical double agents, hiding in plain sight. But now you know the rules, you know what signs to look for. So the question is, what other compounds out there that you thought were purely ionic are actually hiding a covalent secret?